Hi there, welcome to this lecture series on matrix algebra. This is lecture 34. The topic is singular value decomposition, and the second lecture on the same topic, and this is part 1. So in the previous lecture, we introduced the SVD, singular value decomposition. We state the theorem and went through a pretty lengthy proof. And now we will go through some examples and some applications. Let's get started. Let's briefly review the theorem on singular value decomposition. So the statement is the follows. Let A be an m by n matrix, and then n and m are possibly two different numbers. Then we will set P to be the smaller one of m and n. Then there exist following three sets of things. 1, an orthogonal matrix U consisting of vectors U1, U2 to UM, m of them. And second, an orthogonal matrix capital V consisting of V1, V2, and Vn. And third, non-negative numbers, sigma 1, sigma 2 to sigma p, and they are sorted from the largest to the smallest. They are all non-negative. These are the singular values of the matrix A. Then these three things exist such that if I do the product, ut times A times V, it will exactly equal to the diagonal matrix D, where on the diagonal are these singular values, sigma 1, sigma 2 to sigma p. So as a consequence of this relation, we can now write A in terms of the others. So A would be U times D times V transpose. Using that theorem, it is also very useful to realize the following. That is, the matrix A now can be written as the product of these three matrices. So here we take an example where n is less than m. So meaning a number of column is fewer than number of rows. And in this representation, the sigmas here, in particular, if you take square of them, so sigma 1 square, sigma 2 square, they are still sorted from large to small. So these are the eigenvalues of ATA. The vectors here, V1, V2 to Vn, they are an orthogonal basis of eigenvectors of this matrix AT times A. So this is a symmetric matrix, and therefore the eigenvectors form an orthonormal basis. And the vectors Ui here can be computed as 1 over sigma I, A times Vi, for all the i's where the sigma I is bigger than 0. And then the matrix A here can be recovered once you are given these vectors and these singular values as follows. Basically, you carry out this product of these three matrices, and you realize that for each singular value here, it can involve a term U and another term V with certain index. Okay, so you will have a summation I from 1 to n of sigma I times Ui times Vi transpose. So one important note is the following. In this summation sign here, you only need to summing over all the terms when the sigma i's are strictly bigger than 0. And there will be quite some of them will be 0, and those you never need to compute. Let's now take an example. Let's say we have a matrix A, which is like this, rectangular, and we want to find a singular value decomposition for this A. So this calculation would take several steps. Step 1, we need to find eigenvalues and also normal basis of eigenvectors for the matrix A transpose times A, which is a symmetric matrix. So let's calculate this product. And working out the details, you see you get that. You get 10, 2, negative 3, negative 3. So you see that it is a symmetric one. And then we can form the characteristic polynomial to compute the eigenvalues of this matrix. And then work out, we get that. And then we can find the eigenvalues, which will be the singular values. So you find the roots for this. So one is 11 and the other is 1. Those will also be sigma 1 square and sigma 2 square. And using that, you can find the eigenvectors and carry out the calculation. You will get a v1 and a v2 looking like this. And note that they are normalized such that the norm of v1 and v2, they are both 1. Okay, so let's summarize. Now we have the singular values, sigma 1, sigma 2, by taking the square root of the lambdas. And then we can compute the other vector, u1 and u2, using the formula. u1 is 1 over sigma 1 av1. So put in the numbers, 1 over sigma 1, a, and v1, and you work out this product, and this is what you get. So it's a vector of length 3. And then you calculate u2 in a similar way. It will be sigma 2 here and v2 here. And working everything out, and this is what you get. So now we see that we also need to find a third vector, u3, so that we have u1, u2, u3 is an orthonormal basis of R3. We already have u1 and u2, but we don't have a u3. To find u3, we use the property that it is perpendicular to both u1 and u2. So we can write out the constraint. Let's write u3 to be x1, x2, x3, and then you can compute u3 dot u1, which give you this number, shall be 0. And then you can have u3 dot u2, the inner product between these two, shall be 0. And then we have two equations. So you can find a non-zero solution for that, and then you can normalize it to make the norm to be 1, and then you'll get a u3, which is this expression here, and you see that the length of this vector is 1. Now we can put everything together, and so we'll have A matrix here would equal to this U matrix times D and times V transpose. And we can write out each element here. So square root of 11 will be associated with U1 and V1 transpose. And then 1 will be associated with in U2 and V2 transpose, like that. Okay, let it be clear. Let's write out this is the U1 and this is the U2 and this is the U3. And then we have V1 is this and V2 is this. And all these are taken from previous calculations. Now let's verify if this expression is true. So A is this, and then we want to calculate it as what we indicated in the previous slides, that is sigma 1 u1 v1 transpose, and then sigma 2 u2 v2 transpose. Okay, so let's put in all the numbers, and square root of 11, and this is u1 and this is v1, and then this is u2 and this is v2. And then 11 will cancel this 110, you get a 10. Square root of 10 times square root of 10 is 1 over 10. And we copy the rest. And then here you see square root of 10, square root of 10 is 1 over 10. And you copy the rest. Okay, so we can now carry out this product. and this vector times that vector, and then you get a matrix. And also this vector times this vector, you get a matrix. And then you can add them up and you get that. And then you see that if you divided everything by 10, you get 3, -1, 0, 1, 1, 0, which is the A matrix. Okay, so for this simple example, we worked out the singular value decomposition, and we verified that it is a correct decomposition. So this is end of the first part of this lecture. In the second part, we will go through applications of this theorem. So I hope you enjoyed it, and I'll see you soon.